Welcome to our exploration into the mysteries of the universe. Welcome to the new episode of Mystery Connections. The question that has captivated scientists and philosophers alike for centuries: where did life come from? Is it a product of cosmic happenstance, born out of the primordial soup of our Earth? Or does its origin lie in the vast, seemingly infinite cosmos? Some theories suggest that life, or at least the building blocks of life, may have been delivered to Earth from outer space, hitching a ride on comets or meteoroids. A fascinating thought, isn't it? Today we dive deep into these theories, exploring the possibilities and the experiments that have tried to unravel this cosmic mystery. From the early experiments of Stanley Miller and Harold Urey to the more recent discoveries, we will journey through time and space to probe the origins of life. So fasten your seatbelts as we embark on this mind-bending journey. Ever wondered where life originated? How did the first building blocks of life come about on Earth? Delving into the origins of life is as thrilling as it is intricate. Picture the Earth, a young planet in the vast expanse of the cosmos, stirring with the potential for life. But how did it all begin? Theories abound, hypotheses are plentiful. Some suggest life sparked spontaneously from the primordial soup of Earth's early atmosphere. Others propose a celestial origin. In the middle of the 20th century, a groundbreaking experiment was conducted by Stanley Miller and Harold Urey. It shook the world of science, hinting that life's building blocks could form spontaneously under the right conditions. Yet the puzzle remains incomplete. Early Earth had different conditions, and the experiment, though revolutionary, didn't produce all the vital components of life. To understand this better, let's travel back in time to 1952 at the University of Chicago. In 1952, Stanley Miller and Harold Urey embarked on a groundbreaking experiment. This experiment, known as the Miller-Urey experiment, was a bold attempt to simulate the conditions of Earth's early atmosphere and to test whether the building blocks of life could have spontaneously emerged from such an environment. Miller and Urey took a mix of simple chemical substances, water, methane, ammonia, hydrogen, and carbon monoxide, but notably no oxygen, and placed them in a closed system. This cocktail was meant to mimic the hypothetical atmosphere of a young Earth. They then introduced electrical discharges to this mix, a simulation of the energy supplied by lightning in thunderstorms. The duo then sat back, letting time and nature take their course. After some time, they found that their concoction had produced a variety of organic molecules. Among these were amino acids, the very building blocks of proteins, and by extension, life itself. This was a momentous discovery. For the first time, it seemed that under the right conditions, life's essential components could form spontaneously. But what does this mean in the grand scheme of things? The Miller-Urey experiment provided a tantalizing glimpse into how life could have originated on Earth. It suggested that, given the right ingredients and conditions, it was possible for the inanimate to give rise to the animate, for life to emerge from non-life. However, this groundbreaking experiment was not without its caveats. Geologists later showed that Earth's early atmosphere was likely different from the one that Miller and Urey had simulated. Additionally, while their experiment did produce amino acids, it did not yield carbohydrates or lipids, other vital components of life. Despite these limitations, the Miller-Urey experiment remains a landmark in our quest to understand the origin of life. It was a stepping stone, a spark that ignited further research and pushed us to look deeper, question more, and imagine the unimaginable. But wait, this was not the end of the story. The Earth's early conditions were quite different. Contrary to the conditions in the Miller-Urey experiment, early Earth had a different environment. Picture a world swirling with volatile gases, far from the calm, life-supporting planet we know today. It was a wild, untamed landscape where the air was thick with the water vapor, carbon dioxide, and nitrogen, among other gases. But notably absent was a key player from the Miller-Urey experiment: oxygen. The Miller-Urey experiment's atmospheric recipe included methane, ammonia, hydrogen, and carbon monoxide, all crucial ingredients in the primordial soup theory. However, evidence from the geological record suggests that early Earth's atmosphere may have contained less methane and ammonia, and more carbon dioxide and nitrogen. Now, let's talk about the missing pieces of the puzzle: carbohydrates and lipids. These are crucial building blocks of life that the Miller-Urey experiment didn't produce. Carbohydrates, the sugars that fuel life, and lipids, the fats that provide structure to cells, were conspicuously absent from the experiment's results. Fast forward to the present day, and our understanding of chemistry has expanded. We now know that carbohydrates can be formed from formaldehyde through a process known as Formose reaction, while lipids can be synthesized from simple hydrocarbon precursors. But the big question remains: where did all these chemical reactions take place? The Miller-Urey experiment suggested a primordial soup, but the conditions on early Earth were likely far from ideal for such a soup to exist. The environment was harsh, with frequent volcanic eruptions, meteorite impacts, and drastic temperature changes. It was hardly the kind of place you'd expect delicate biochemical reactions to take place. In the face of these challenges, it's clear that the conditions on early Earth were not as conducive to the formation of life's building blocks as the Miller-Urey experiment initially suggested. So, if not on Earth, where could these building blocks have come together? Could life have originated in the vast expanse of outer space? An intriguing thought, isn't it? The possibility of life's origin in space is an idea that has piqued the interest of scientists worldwide. There's a growing body of evidence that suggests that the building blocks of life, the very ingredients necessary for life as we know it, may not be exclusive to our home planet. In the infinite cosmic playground, scientists have indeed stumbled upon some of these essential building blocks. We've found amino acids, the building blocks of proteins, in meteorites that have crashed onto our planet. These extraterrestrial visitors carry with them the whispers of the cosmos, revealing secrets about the universe that we're only beginning to understand. But the plot thickens. A team of Canadian scientists recently embarked on an experiment that takes this hypothesis a step further. They decided to recreate the conditions of space in a laboratory, subjecting raw materials to a bombardment of low-energy electrons. These electrons, released by the ionization of matter by radiation, are abundant in the cosmic landscape. The results, they were more than promising. The scientists managed to produce glycine, a simple amino acid, under these simulated space conditions. Now, this might not sound like a lot at first, but let's put it into perspective. Glycine is a fundamental building block of life, and the fact that it could be produced in conditions mimicking outer space is a significant revelation. It suggests that the building blocks of life could indeed form in the harsh conditions of space and eventually find their way to a planet such as Earth. As Michael Hewells, one of the scientists involved in the study, puts it, you have to remember, in space, there is a lot of time. The sheer timescale of the universe provides ample opportunities for these molecules to form. So, could the seeds of life have been sown from the stars? The answer remains elusive, but the possibilities are certainly tantalizing. Let's delve deeper into this exciting study. Glycine, a simple amino acid, could it be the key to life's origin? Let's delve deeper into the intriguing glycine experiment. A team of Canadian scientists sought to answer this question. They started with a simple premise, an experiment that would mirror the conditions of outer space. They exposed raw materials, the building blocks of glycine, to a barrage of low-energy electrons. These electrons, released by the ionization of matter, mimic the radiation found in the vast expanse of the cosmos. The scientists observed the reaction rate, and it was nothing short of remarkable. It was so high that realistic quantities of glycine were produced. This experiment suggested that the formation of glycine or similar biomolecules in space isn't just a wild speculation, but a plausible reality. But why is this significant? Well, glycine is an amino acid, a crucial component of life as we know it. It's involved in the creation of proteins, the building blocks of our bodies. If glycine can form in space, it opens up the possibility that life's building blocks could form outside our planet and eventually be deposited on a planet like Earth. This thought is further supported by the words of Michael Hewells, one of the scientists involved in this experiment. He reminds us that in space, time is abundant. The formation of biomolecules like glycine could have been happening for billions of years, slowly but surely paving the way for life. While this experiment isn't definitive proof that life originated from outer space, it's an intriguing piece of the puzzle. It shows us that the universe is a vast laboratory, capable of creating the building blocks of life in the most unexpected places. This experiment, like the Miller-Urey experiment before it, pushes the boundaries of our understanding. It challenges us to look beyond our planet and consider the cosmos as the cradle of life. We may not have all the answers, but each discovery brings us closer to understanding the origins of life. The origins of life continue to be one of the biggest mysteries of science. We've journeyed together through the intriguing Miller-Urey experiment that showed us the possibility of spontaneous formation of life's building blocks. We've delved into the early conditions of Earth, which challenged the results of the experiment. We've pondered upon the possibility of life originating from outer space and have seen how scientists have already discovered simple building blocks in the cosmos. And we've seen how a team of Canadian scientists have proven that even amino acids like glycine can form in space. These scientific strides are monumental, yet the puzzle remains incomplete. The quest to understand our origins is far from over. It's a journey filled with endless curiosity, boundless possibilities, and countless theories. It's a testament to the unwavering human spirit to understand the world around us. So next time you look at the stars, remember, we could all be stardust.